We have seen the Earth from afar and have realized that we are all passengers on a lonely spaceship around the sun that's with light and energy. Studying the Earth from space may yield the greatest dividends from our manned spaceflight capability. With the exploration of the moon as a goal, we have created the basic technology of manned spaceflight. We know that men in space can observe and make decisions, conduct experiments, operate instruments, make repairs and adjustments. They can contribute in many ways to the improvement of life on Earth. In fact, they can greatly expand our knowledge of the sun, the moon, and the entire universe. But to do that most effectively, we must learn how to extend man's residence in space, determine what needs to be done, the full scope of tasks that men can perform, the best way to perform them, what instruments are needed, and how to build them. These will be major objectives of NASA's first manned space laboratory, Skylab. Skylab will be launched in 1973. Three-man crews will live and work in Earth orbit for weeks at a time on separate missions over a period of several months. They will collect experimental data on behalf of many of the world's foremost scientists who conceive the experiments and will interpret the results. The Skylab program uses much of the Apollo hardware. For instance, the laboratory will be launched by the first two stages of the Saturn V vehicle shown here in its Apollo configuration. Within the space that would normally be the rocket's third stage, most of the Skylab components will be assembled prior to launch. Three of the smaller Saturn 1B vehicles will be used to transport three separate crews to the laboratory. The Saturn 1Bs will be launched from Pad B of the Saturn V launch complex. Being smaller, they will be mounted on and launched from a pedestal. All vehicles and payloads will be assembled in the huge vehicle assembly building and transported vertically to the launch pad. The Launch Control Center, built for the Saturn V, will be used for all four launches. The laboratory will be launched first and placed into a near circular orbit at 235 nautical miles altitude and a 50-degree angle with the equator. This high angle permits Skylab to fly over all of the United States except Alaska, and in fact over about 75% of the entire surface of the Earth. After reaching orbit, the protective fairing is jettisoned. The craft is stabilized, and the telescope mount is rotated to point the telescopes toward the sun. Solar panels are folded during launch, then deployed in orbit to convert sunlight into electricity to operate the telescopes and provide power for the rest of the laboratory. Next day, a Saturn 1B is launched with the first three-man crew in an Apollo spacecraft adapted to this mission. The spacecraft is maneuvered into an orbit that permits rendezvous and docking with the laboratory. The men transfer to the workshop and begin their missions. 28 days for the first one, 56 days each for the second and third. Skylab will fly unmanned between missions. The living areas and primary work areas of Skylab are on two levels within the orbital workshop. Using mock-ups, we can see some of the details. On this level, there are 4 rooms. This is a ward room where the men will eat and relax. A window will provide a spectacular view of the Earth when on Earth's sunlit side. It will be double-paned with glass of high optical quality. Heaters will keep it from fogging. During off-duty hours, the men will enjoy reading, listening to taped music, to radio transmissions from Earth, and will communicate with their families. Food sufficient for 140 days of manned operations will be stowed prior to launch, most of it in these lockers. The food management area of the wardroom is similar to an earthbound kitchen. Special trays will warm the food, and the men will eat from them much as do commercial airline passengers. For privacy, there are 3 compartments for sleeping. Sleeping bags have adjustable restraints. Since being weightless, the men will tend to float about. In 0G, there is no up or down. Garbage, waste paper, soiled clothing, and so on will be bagged and placed into a storage tank. This is the bathroom. Primarily, bathing will be done with a hand sponge, but other methods will be tried. Samples of urine will be frozen. All fecal matter will be dried. Both will be stored in containers and returned to Earth for analysis. The excess urine and water will be bagged and placed into the storage tank. The floor and ceiling are made of open mesh, primarily to allow for good air circulation. Specially designed shoes hook into this mesh to provide body restraint, since in 0G, without them, it is difficult to stay in one place. This is a mock-up of the airlock, which provides a 5.5-foot pressurized tunnel between the workshop and multiple docking adapters. In addition, as its name implies, it provides an airlock so that men can move outside the laboratory and re-enter without losing pressure inside. Tanks store the nitrogen and oxygen needed for breathing during the entire period of manned operations. Equipment and controls for keeping the air fresh and circulating are located here. Electrical power from the solar panels is brought here and distributed to the entire laboratory. The primary consoles and displays for the communications systems are mounted here. The main purpose of the multiple docking adapter, of which this is a mock-up, is to receive the spacecraft that transport the crews to and from the laboratory. The main docking port is at the end, and there is an emergency docking port on the side. But the docking adapter is also a workstation. It has a window of high optical quality for precise photography of the Earth, and will have instruments and controls for many Earth observations. The control station for the solar observatory is located here. From this station, an astronaut scientist will scan the sun, train the telescope mount, and record the sun's radiation. Approximately 50 scientific investigations will be performed during each mission. Here are a few examples that serve to illustrate their type and scope. At intervals during each flight period, the metabolic rate of each astronaut will be measured at rest and when performing a calibrated exercise on a bicycle ergometer, which records the energy being used, while a metabolic analyzer records the volume and constituents of exhaled breath. These tests will show how prolonged weightlessness affects breathing and measure the energy consumed by physical activity. Determining weight in a weightless world is a real problem. With no gravity, there is no weight, and normal scales cannot be used. But there is mass, and many of our biomedical experiments require its measurement. For measuring small masses in Skylab, this device will be used. Using a known mass, the device will be calibrated in flight and later used to determine the mass of food intake and of excrement. The object to be measured is placed in a holder held by a rod suspended on a spring. By releasing a lever, a pendulum cycle is set up. The time of each cycle is precisely measured and is proportional to the mass of the object. The device is so sensitive, it can even weigh a postage stamp. This odd-looking chair will be used to weigh the astronauts. It works on the same principle as the small device, but the man sits in as immobile a position as possible, even holding his breath. In this experiment, the split seconds are monitored and displayed electronically. The time it takes for the pendulum motion is recorded, and from this, the subject's mass is calculated. The chair is restrained by a spring. Here, too, a slight mechanical push establishes a pendulum action. The greater the mass of the subject, the slower the movement of the chair. Before and after each mission, extensive tests will be made on each astronaut to determine body changes such as loss of calcium in his bones, deterioration of his muscles, changes in blood circulation and constituents. Extensive baseline data gathered in simulated Skylab conditions on Earth will be used to compare with actual Skylab medical findings on many zero-G reactions of the human body. From spatial orientation to motion sickness. Other biological investigations will be made using pocket mice and vinegar gnats to study the effect of prolonged weightlessness combined with the removal of the normal 24-hour day-night cycle to which all life on Earth is subjected. What is the mechanism that causes daily rhythmic changes in temperature, pulse rate, and other life processes? This equipment will be used to study the effects of prolonged weightlessness upon individual human cells. In the black box are laboratory instruments skillfully miniaturized for use on a spaceship. On the right is a regular Earth laboratory microscope, camera, and lamp. On the left, the Skylab equivalent takes up a small space inside the container. In one compartment of the compact box are two cameras with lenses magnifying 20 and 40 times, with lamps, 16-millimeter motion picture films, and a motor to move the film in front of the lenses. The human kidney cells to be photographed are in two chambers at one end. At regular intervals, time-lapse motion pictures like these will be taken. They may reveal zero-gravity-induced changes in cell behavior, such as in the reproductive process. The living cells are fed nutrient pumped in through tubes. They will be returned to Earth for continuing observation. In the compartment on the other side of the container are two assemblies of biopacks, each holding thousands of human lung cells at normal body temperature. At preset times, the Skylab astronauts will operate controls to fix these cells in order to preserve them at various stages of their growth. All the cells, fixed and living, and the exposed film will be brought back to Earth, where individual cells will be carefully studied for any changes from the norm, for instance, in their chromosomes or metabolism. All life is influenced by gravity. By removing gravity from living cells, the simplest units of human material, scientists hope to find new clues to the nature of the life process. To learn more about the sun, extensive studies will be made during the entire Skylab mission. The Solar Observatory is the most complete ever placed in space. It includes a specially designed telescope mount that will point the telescopes precisely to selected areas of the sun and the gases that surround it, and hold the entire laboratory steady while the radiations are being observed and recorded. 8 telescopes are mounted within a cylindrical shroud that will have a liquid cooling system to keep the entire assembly at a constant temperature. Through these telescopes, measurements of solar activity will be made simultaneously in different wavelengths, in white light, ultraviolet, and X-ray regions. Most of the data will be recorded on film, some on tape. Exposed film will be recovered by astronauts going outside the laboratory, and unexposed film inserted into the cameras. Film will be returned to Earth for processing and analysis. The tape data will be transmitted to Earth by telemetry. The sun is a giant, restless, churning thermonuclear furnace that sends out radiations at various wavelengths in ever-changing intensity. By recording and analyzing them, we can deduce what's happening there. And someday, we may be able to do the same thing on Earth for the generation of electrical power. The area from its surface out to about 6 sun radii, almost 2.5 million miles, will be studied intensively to determine how energy is transferred through it. The surface of the sun is about 10,000 degrees, but the corona, the envelope of fiery gas that surrounds it, is about 2 million degrees. How does a surface so much cooler generate such extremely high temperature? We hope to find out. Special attention will be given those violent explosions called solar flares. What causes them? What is the source of their energy? How does the energy get out? Why do their frequency and intensity vary according to an 11-year cycle? How do high-energy solar radiations reaching the upper atmosphere affect the Earth's weather? The big flares don't happen very often, and happen with little or no advance warning. The Skylab astronaut will see the entire sun on his display and detect these flares when they are just starting. Within seconds, he can have the telescope cluster pointing at that area. He will have spent hours in training for these precise operations. He will be in direct communication with the principal investigators on the ground, who, in turn, can quickly consult with various ground observatories around the world when their detection of solar activity requires Skylab's closer look. The sun dominates the entire solar system and is the single most influential element that affects life on Earth. Skylab will provide an unprecedented opportunity to study its radiations over a long time period without the screening effect of our atmosphere. We will gain experience in operating a complex set of instruments in Earth orbit. This will help us build future scientific laboratories and observatories for operation in space. In another area of research, instruments of various types will be extended through scientific airlocks into outer space, in some cases as far as 18 feet at the end of a boom. These instruments will be observing and measuring such things as meteoroids, micrometeoroids, water vapor, particles that can contaminate optics, cosmic rays, and solar activity. This experiment, furnished by the government of France, will scan large segments of the heavens for ultraviolet radiation. Another one will determine what happens to ultraviolet as it passes into the ozone layer of the atmosphere. Various experiments with materials and processes will also be tried on Skylab missions. Experiments never before possible will be conducted in the sustained zero gravity. Here are crystals growing in a laboratory on Earth. Their growth seems to be shaped and limited by the effects of gravity. In the Skylab experiment, a single crystal in solution inside a sealed container will be placed inside the chamber and its temperature monitored during the mission. It is hoped that near-perfect crystals can be produced in a weightless environment that will have extensive value in science and industry. Similarly, it is believed that almost perfect spheres can be made in zero gravity. When a metal sphere is formed on Earth, the weight of the molten metal leads to distortion as it solidifies. A sphere which does not require machining to make it perfectly round has many industrial and technological possibilities. Other experiments in the zero-G chamber will reveal more about how a flame reacts in a zero-G environment, where there is no gravity to cause convection currents. Several different kinds of material will be ignited, observed, and photographed by the astronauts. For fabrication or repairs in space, can welding or tube joining be done using an electron beam or other heat source of a kind that does not cause melting, which is hard to control without gravity? Can totally new compounds be created if molecules can be freed from gravity in the formative stages? Skylab will just be able to touch upon a few of the possible uses of zero-G, but it'll be a start. The ultimate promise in nature's gift of this new dimension cannot yet be foreseen. The Skylab Earth Resources Experiment Package includes 5 different kinds of sensors for studies of a variety of Earth conditions, from measuring moisture in the soil to identifying contamination in large bodies of water, from detection of underground and under-ocean rivers and springs of fresh water to the heat output of cities and the design of even more advanced microwave, radio wave, infrared, and similar scanners for the future. Extensive tests will be made in sensing and recording the different patterns of light and heat radiated by different types of Earth terrain. One such experiment will be to photograph portions of the Earth in several wavelengths simultaneously. And to do it for many types of surfaces. The objective will be to determine what film and filter combinations provide the best data for surveying Earth resources. Teams on the ground will survey selected areas to determine exactly what's there. This will assure accurate interpretation of the data recorded by air and space scanners and identify and confirm the unique signatures revealed by such differing areas. Skylab's role in developing instruments and techniques for such studies is an indispensable link in our nation's total Earth Resources Survey Program, which will use aircraft, ground research, and unmanned satellites, especially the Earth Resources Technology Satellite, as well as Skylab, with several government, university, and private industry groups cooperating. People in many diversified occupations will gain valuable knowledge from Earth resource studies when the technology is fully developed. We shall be able to make a worldwide agricultural census every few days and detect the spread of crop disease in wide areas in time to do something about it. A single snapshot from one of the Skylab cameras will cover 6,400 square miles in 5 different wavelengths. We shall get advanced information on feed and pasture. And shall get current data on the locations of migrating fish. Such techniques may lead to increased abundance in the world's food supply. Finally, but not least important, our youngest citizens will benefit from their personal participation in the Skylab program. Some activities and experiments to be performed by the astronauts are being proposed by students in school projects across the country. Television broadcasts and tapes from Skylab are planned to bring selected activities directly into the classroom while they're being carried out. NASA is providing America's first experimental space station to open new opportunities for research and applications that will enrich the lives of all the billions of people on Earth.